Over the past 30 years, the whole world of computer graphics has been achieved using triangles and textured meshes. But just a couple years ago, that whole paradigm changed with the invention of radiance fields. And what is that? That's basically representing the scene with a bunch of these special blobs that changes appearance as you move around. Sounds simple, right? But it's really actually complicated. And in this episode, we're going to bring an expert on, Ruilong Li, who's a researcher at NVIDIA and a former student at UC Berkeley, where he created some of the foundational components for 3D Gaussian splatting. He's going to teach us how this all works, how to get good images, and we're going to become ourselves experts in 3D Gaussian splatting. And always, we're going to be joined by my co-host Jared Heinly, where he's going to take some of these really complex topics like backpropagation and help us demystify those terms so you can even understand what's happening. So without further ado, let's jump into this latest episode of Computer Vision Decoded. Welcome, Ruilong, to the episode, and welcome again, Jared, as always. I'm really excited about this episode. When we did an episode, I think it was our 6th episode, we talked about NeRFs with Matt Tancic, and it was a really big episode for us because it was something that a lot of people see visually, NeRFs, and it's interesting, and they really want to learn how this works or what they're actually looking at. And since then, I mean, we'll get on this, but NeRFs kind of aren't the popular form of radiance fields. It's now to Gaussian splatting. And so we wanted to make sure we had an expert on here to help explain what all this is all about. So Ruilong, that's why we have you on here. I know you've been involved. In fact, I believe you did research with Matt at UC Berkeley, and you have quite a bit of history in this. And so just to give us a little bit of background before we jump into Gaussian splatting and the world of computer vision, can you just give us like a quick overview of your background? What interested you early on, in either as a kid or maybe in college, to want to go down the route of learning about computer vision, 3D reconstruction, NeRFs, all this?
Yeah. Thanks for having me. It's pretty excited to be here joining this conversation. And for me, I started doing research like 6-7 years ago. But when I started as a researcher, like a junior researcher, I didn't work on 3D problems at all in the beginning. It was just a pure 2D researcher working on those images and like doing some image perception tasks like detection, segmentation. But after like a couple projects, I start to realize, okay, some of the problems in the image domain are pretty hard to solve by only look at clues from pixels. So for example, there's like a detection segmentation, like when there are severe occlusion happen on image, it's pretty hard to kind of distinguish like different instance on just the image domain. And I start to think of like a better solution, like more principled one. Like I'm thinking like maybe we could just lift things back to 3D. And for those questions, specifically like occlusion, it could easily like distinguish different instances in 3D if you could lift it back. And so that's where I start to shift my interest into 3D. Okay, so the first question is how to lift the image back to 3D. So we started with some like deep learning based technology, because back then it was like the starting phase of the deep learning neural networks, and doing some training on some annotated data. Then the question is, okay, where do we get those annotated data with the 3D labels? That's pretty hard to get. Even now, we don't have too much like labels in 3D. So it was pretty toy scale at the time, training some models to do the prediction, lifting the things into 3D. And so that was around the time that NeRF actually came out. It's like 2022, I think. And it first came out, it just shocked me quite a bit. Like it just got everything so sharp and so high quality. And so then I started to realize, okay, instead of doing this like deep learning based solution, we also have another set of solution, which is kind of this optimization based from multi-view images. So then I start to basically jump into the NeRF field, look into, okay, how does this work, and what are the things that we are not happy with, we could improve. So the biggest part at the moment was its runtime of the NeRF is pretty slow, like has to train for 24 hours, like over a day to get a single reconstruction on this Lego data. And rendering it took like 30 seconds a frame at the time. So it was super slow to do the development and trying to discover, okay, how good it performs on those real data. So I spent quite a few time on quite a couple projects on this efficiency aspect of the NeRF, trying to improve at that. And also a couple projects on the side trying to apply NeRF to dynamic objects. And then Gaussian came out like in at the end of 2023, I think, and it was another shock, like just so fast, like both the training and the rendering is just 100 FPS, like viewer easy, real-time viewing easily experience. So then I start to look into Gaussian splatting, see what's the magic there, and start to implement things, because that's how I learn things, just implement things from scratch. That's how I be confident that I know all the details there, and end up having this like Gsplat and also the Nerfstudio. We also developed that in the beginning for NeRFs as well. So yeah, that's kind of the journey of me getting into this like 3D field and end up doing some research on the Gaussian splats.
Interesting.
That's awesome. And it's neat to hear that you said like the transition, you said you started out focusing on 2D image tasks, segmentation or detection, but then saying, oh, well, it'd be nice if we had some 3D context here. And now transitioning into, well, how do we actually generate or represent that 3D information?
Yeah,
that's
cool. 3D is cool. Like looking things in 3D is way cooler than just looking at pixels. So it's a different experience.
I agree.
What's interesting too was you said like early on, and we talk about timescales. If you look at your research resume of like the projects you've been involved in, I mean it goes back to 2018, but really like 2019, 2020, you're doing 2D. It's just the acceleration from what was available in 2020 versus 2000 last year. It's incredible the pace at which
exactly
this has evolved
too fast.
Think about sciences, how they have breakthroughs that come every once in a while, and it's all of a sudden we hit breakthrough after breakthrough in the fields of 3D, computer vision, AI, all these all at once. So I felt like the first half of my career, in fact, here at every point, it was things move slow, and then all of a sudden it's like someone put their gas on the accelerator, and it's just a game of trying to stay relevant and keep up with the advances.
Yeah, like 4 years ago, before I started my PhD at UC Berkeley, nothing works. Like nothing is working except this like facial detection system. But now it seems like everything is working. It's just crazy time.
Mm-hmm. Yeah. Just to touch on that, even Jared's been amazing for us, because when he joined our company, things were taking half a day to process on servers for data sets. And now he's got it optimized to run on mobile devices in seconds. And so the fact that we are doing practically the same, we're getting the same answers or the same output, might not be exactly the same, but we're achieving our goal on device, on edge, at a much greater speed, just means it's more tangible for everyone. That's like NeRFs. When I first came out, I remember seeing like there was like a NeRFy project that came out, and it was cool. And then they were like, okay, we trained this on, I don't remember what the GPU was at the time, but it took 3 days. And it's like, well, that's not something that I can even try, let alone would have the patience for. And then it went from that, it went from days to minutes, almost overnight at one point. So all right. So then let's transition to then like the main reason we wanted you on here. So we've never done a Gaussian Splat episode. I know so much about it. I think a lot of people learn about them through my social media and YouTube and all that. However, I mean, I kind of take it through the lens of, you said you like to play with projects, play with code, see how they work. That's how I've learned, but I don't come from the science base of this. I'm more of I've played with it and I've talked to enough researchers to understand it, I believe, but I want to hear from you. I want to hear from an actual researcher who has, built this technology and implemented it in some fashion. And so imagine this is the first time someone heard Gaussian splatting. Maybe they've seen a video of it, but they didn't really know what it was. Can you explain what they're seeing? What is it? What is Gaussian splatting? Not necessarily how it's made step by step, but what are we looking at here when we look at one of these cool renderings?
Yeah. So in a short way, I would summarize the Gaussian splats as involving two parts. One is the Gaussian, one is the splatting. And the Gaussian itself is a representation of 3D, is basically some like Gaussian blobs that we use to represent a 3D environment. And the splatting is a way that we render those like Gaussians in 3D into a 2D image. So together, this is a kind of a system that give you a way to view the 3D in real time, like pretty fast. But not only that, also give you a way to reconstruct the 3D, because this entire representation and the rendering process is differentiable and easy to be optimized. So this entire build up a system that you could lift the signals from pixels back to 3D and view it by rendering the 3D back to the image plane.
Okay. So almost like a little bit of visual trickery going on. You have a 3D world being projected 2D. I think that's one concept a lot of people struggle with, is that it's not looking at necessarily a 3D object. It's just a 2D rendering being updated tens of times, hundreds of times per second in their screen.
Yeah, like in the old times, we have this mesh as a representation of 3D, and we render mesh. Probably more people are familiar with that, but now it's kind of like a new representation that is similar to how mesh is functional in 3D, but now we have those Gaussian blobs, and the rendering attached to those new representation kind of changed from this mesh, what was being applied to mesh, to this new stuff called splatting applied to those Gaussian blobs. It's kind of cool because those rasterization. So the splatting part, we also call it rasterization at some point. Those technology also kind of exists for a long time. Those technology also applies to other representations in 3D. But the nice parts in the current phase is that those rasterization process are differentiable, which means we could use them as a bridge between and to optimize and recover the 3D from 2D image through this like training or optimization process.
Interesting.
Sweet.
Okay.
I want to break that down a little bit. So you mentioned talking about a mesh. So people may be familiar with a mesh representation. So for example, suppose I've got a really simple wooden desk, in front of me, and it's just a rectangle. And so, and it has some thickness. And so maybe it is just 8 vertices, 4 on the top of the table, 4 on the bottom of the table. I've now got, just a limited set of triangles. I got a really big, the top of my table is just 2 big triangles. But then now to get that nice wood texture on top, I'm using some image. So there's some image that then is mapped onto that triangle mesh to create that nice wood texture, nice wood appearance. If I now think about this wooden desk, this wooden table in a Gaussian splat, what does that look like?
Yep. Those are just some Gaussian blobs kind of stacked together like into this it's kind of like a Lego. Actually, Lego is just different pieces, and you stack them together and build up some like 3D object. And instead of those Lego pieces in Gaussian splatting, it's just some Gaussian blobs, spheres, that you use to build up those objects. And those spheres carries colors, carries like things we call opacity, which is like how transparent it is. Also carries some like additional informations in those blobs. Things like, okay, what the object is it a table or is it a chair? Some semantic information like we could also carry it on those like blobs. So those becomes like the basic elements of 3D, and we use them to build up 3D. So that's just the Gaussian stuffs.
Got it. So okay, so if each blob has its own color, and then so now that means, so like on my table, if I've got all sorts of browns or yellows or different shades of that wood color, then does that every time there's a change in color, that means there's a different blob, a different Gaussian there representing that in the surface?
Yeah, mostly true. Every time like the texture changes, there will be some new blobs trying to represent that texture, and those blobs could also change shape. Like could be like very skinny type of shape, or it could be very flattened, like represent a single large surface. For example, the wall on your back probably could just be represented by a couple large blocks. And for those textures on the wooden kind of table, you would have some like a lot of like tiny skinny Gaussian blobs to represent those. And by stacking all those blobs together, you get this entire environment represented.
Nice. So like what's a typical, so like if I had a table, that has some wooden texture on it, or, is that hundreds of blobs? Is that hundreds of millions of blobs or Gaussians?
Yeah, typically it's around of the level of a million or at least a couple 100,000 Gaussians to represent environment with faithful details. But that also depends on like how much detail we have in the scene. So for the single table specifically, if we take it as an example, like a single table, I would say like 1,000 to 10,000 Gaussian blobs could represent it pretty well.
Yeah, that's awesome. Yeah. So going back to your Lego example, it's lots. Yeah, each of these blobs is like that little building block, like a pixel in an image, but now it's some shape. You said it is Gaussian. You can be long and skinny, or it could be spherical. And just all these things can be combined next to each other to create that appearance of that surface.
Yeah.
Neat.
I can see how you're representing more of a featureless, I think, a wall from a distance where you're not seeing all the little textures of the wall, because even my walls here have bumps and things, but how that could be just maybe hundreds of Gaussians, not hundreds of thousands, because you don't have to have tiny little changes here and there to make that appearance. And so that is one cool thing, is that it does optimize the scene. In some areas it could be really dense, in some areas it could be really sparse, because it doesn't have to be like a uniform number of Gaussians across the scene. It's like NeRF is, which I think they also did some things to do some octree optimization, but it's always kind of like this thing could be really hard to render because it's millions, and this area over here could be really easy to render because it's just the back wall, things like that. So
in a sense, it's also kind of similar to the traditional mesh, where you could have really small triangles on those like detailed regions and really large flattened triangles on the walls, for example. Just a couple triangles could cover the entire wall. So in that sense, they are pretty aligned. Those two have this different level of details, different spatial location property.
And I guess, subtle differences there too, is like with that mesh, it's like if I have a triangle mesh that's textured, it's like the complexity of my geometry is independent from the complexity of the texture and the appearance that I'm putting onto that triangle. And so it's like I could have really simple geometry, but then a really highly detailed texture, which makes it look like it has more detail there. But yeah, there is that trade-off, like you're saying. I'm trying to represent something that has a really complex shape. I need a lot of triangles in order to accurately represent that. Whereas, with the Gaussian splat, my understanding is it's more about just trying to get that appearance, getting an accurate appearance of the scene.
Yeah, that's actually a great point. Like the Gaussian is kind of coupling the geometry and the textures.
Yeah.
Because each Gaussian carries both the geometry information and the texture information. So in that sense, there are also some research going on actually to make it better to decouple this for Gaussian. For example, we could also have a texture map for Gaussians as well, and each Gaussian could just query from that texture map to get what the color information is should carries. But yeah, I think this is something still kind of actively being researched on. People are trying to find better ways, but combining the texture and the geometry in the Gaussian world as well.
Yeah. Awesome.
Okay, so then let's just go a little bit more into then how these are made. And I have some questions that will kind of go around this. Maybe you can answer some misconceptions that people have about how this works. So let's just talk like phase by phase and how or step by step when you're making it. So the first thing, whenever you're creating one of these scenes, is we need images, right? Like you're not making these out of nothing. So what exactly do you need as the input?
Yeah, so let's start with the original Gaussian splatting kind of algorithm because things has been evolved. But if we stick with the original one, so what we need is a set of images that is capturing a single environment or a single object, and we have some requirements for what those images should be should see the same object or the environment from different viewpoints. That's all of this coming from the requirement coming from the algorithm of triangulation. Like if you see the same object from different viewpoints, you would be able to triangulate this object and locate its find its 3D. That means we need a set of images viewing the environment from different view angles, and also the cameras that tells us, okay, the camera information which tells us where those images are being captured in 3D. And the camera information, of course, it involves like the extrinsic camera information, which is like the pose, the rotation, and the location of the camera. Also the intrinsic of those cameras, which is how the perspective distortion look like, basically the focal length of the camera. Like we could get that from the capture information. And some cameras or capture device, when you do the camera, it could give you the extrinsic and intrinsic automatically. For example, iPhone have this IMU sensor that could tells us the camera poses and the location. So we could just use that information along with the images, and those are all the things we need to reconstruct the 3D to create the Gaussians. But some cameras do not have the extrinsic information or intrinsic, so we have to use some external tools to recover that. And one of the most popular one is the CoMap. The toolbox could just take in a set of images as the input and give you the camera poses and the camera intrinsic information of those images. And the best part of CoMap is it also gives you a sparse set of point cloud that recovered in 3D, because it's used those are kind of the intermediate results of the CoMap used to recover the poses, but it generates those things for free for you. And Gaussians could also take advantage of those sparse point clouds, because those sparse point clouds kind of tells you roughly where the objects are in 3D, and we could just start with this sparse point cloud and trying to recover the 3D by building those like Gaussian blobs in 3D. So those are the three set of inputs that Gaussian splatting could accept, and the mandatory ones are the images, the camera poses, the intrinsics, and the point clouds are kind of optional one. Like if you could start with some initial point cloud, that gives you a very good beginning, and you could get the reconstruction better and converge faster. But if you don't have the point clouds, okay, there are also technologies that could help you to recover the 3D, but you could probably expect a less accurate and longer time to get the 3D.
Mm-hmm.
Yeah,
got it. That actually works with how I've played with it. You can seed it. I don't know if seeding is the right word, but like, right, you can initialize the optimization stage or creating those blobs, the spheroids, using your sparse point cloud, which is always the best results I always get. Or you can give it nothing, or you can have kind of like you can just give it a random set of points. So it'll create like a cube with a bunch of sparse points everywhere, and then from there it'll try to map some of those. And so it's kind of basically the same. Once we go to the next step, it's like, say, all of these points start out as a Gaussian. From there, we'll optimize you. Well, you might have a go. So that's another question people often ask. If I have a sparse point cloud, they tend to be noisy. They tend to have a bunch of noise. Is it better to clean up that noise and just start out with like a very clean, sparse set of points? Does that make a difference, or does the optimization stage, all the noise just goes away real fast, and it's just wasted effort, I guess you could say?
Yeah, that's a good question. So all those points are going to just be used as an initialization. And so as long as the initialization is roughly good, it won't make too much difference on like having like, for example, 5% of the points as noise or not. Like those small amount of like points wouldn't affect the entire optimization that much, because it's just initialized from that, and the following training would adjust the location of the points and kill some improper points anyway. So I would say noise is fine. Having some noise is fine in the data, because this entire optimization is pretty robust to handling those noise points.
Tim? Well, on the inverse, it would be better than to, while I'm running ColeMap, I mean, if you guys, we actually haven't, I don't know, real long, if you've watched our videos or listened, we actually have a whole episode on running the sparse structure from motion. But what we didn't cover is then you can go run a dense reconstruction. Would it be more advantageous to then spend the extra couple hours to get a nice dense output and use that as my initialization for training the scene?
Yeah. So having a much denser initialization definitely helps, but only helps from the perspective of converting the point cloud to the Gaussians, like the reconstruction process, the optimization process. I could totally imagine that could shorten your time of reconstruction. You probably only need like half of the time to converge to the same quality by using the dense point cloud to initialize it. But as you said, that also comes with the cost of you have to wait like 4 hours for the ColeMap to give you the dense point cloud. So there is this trade-off here, basically, like whether you spend more time on getting more accurate points in the initial stage, or you spend more time on the optimization part of the Gaussian to get better quality. Because if you give the optimization part longer time and give it more resource to allow it to create more GPUs. Okay, sorry for the noise. All right. To allow it to create more Gaussians on the GPUs, then it will most of the case certainly converts to like better quality. So I would say because like ColeMap, I think is running on CPU. The thing is was designed to run on CPU, so it was slow. So I would say like putting more resource on the later stage using the optimization makes more sense, because it's all on GPU, and with the current implementation that we have, it could be optimized pretty efficiently. So as long as we have some rough structure, I think the sparse points from ColeMaps in most of the case is enough to kick off Gaussian splatting runs.
Well, that's super helpful, because I think there's a lot of confusion over what's the best input. Would you have any additional tips then on imagery? I mean, I always tell people they want sharp images, they want wide field of view, because you're trying to get more context and less just like a really small image area. Yep. And I also tell them that the poses, getting like those camera intrinsics and extrinsics are really critical. Is there anything else you would add on there that you wanted to make sure to, like, if they wanted to get the best quality possible, is there anything else they need to be concerned about?
Yeah, there is a very small trick actually turns out pretty important. For example, if you use iPhone to capture the images, capture the video, it has this by default auto white balance on to give you better visuals. And the auto like exposure adjustment is also turned on. But those things are the things really hard to deal with when we are trying to recover the 3D, because different frames with auto white balancing would end up have different colors on it, different appearance of the same object. So if your goal is to recover the 3D, I would highly suggest to turn off those auto effects on the image. So what I would do is I think the iPhone camera is pretty nice. You could just tap it for like a couple of seconds. It will pop up this option of turning off the auto white balance and exposure option. And turning that off, that's pretty important for the reconstruction.
Okay. It is actually important, probably have some dynamics of the actual scene, like the lighting would be as you move through the scene, you're capturing the lighting as it is and not trying to make this hypothetical perfectly lit.
The dynamic part, the dynamic part is there are algorithms to deal with that, but would suggest to avoid that if we don't want to specifically deal with dynamic parts. Also the shadings, like when I capture like an object, it's pretty easy to have some shadings because of the cameras and the lighting is behind you, and you have this like a hand-holded phone, like have some shading on the tables, and you are trying to capture those, and the shading is part of the dynamic kind of object in the environment that we would like to avoid when we just want to recover the object.
Yeah, get nice diffuse lighting in the room or outside.
Yeah.
Bright but cloudy days if you don't want to capture. I always tell people that's the nice thing about a drone is that if you're capturing something that you could walk around and capture, sometimes the drone's better because you cast this large shadow versus a drone might cast a much smaller shadow that might not be noticeable in the output.
Yeah,
even though you could have walked around it. So there is that. When it's sunny, maybe these tiny drones nowadays, we have pretty good cameras. You could just go fly.
Yeah, drones are pretty good. Yeah.
Okay, so then it goes to this so I get these images, I put them in. Having good poses I know is really important. So using Colmap, using like the best you have for that is important. I know there's all these AI-driven ones that are coming out that aren't hitting the same benchmarks. While they're fast, you might still not get as good quality. So you want that good input. Then it goes to this optimization stage, which kind of, can you explain this? I think this is also something I didn't understand for probably the first couple of months of using this, that it goes through like a cycle. It goes through a loop. It creates Gaussians, then it rasterizes it, and then it references it, and then it goes back and then changes the Gaussians again, right?
Yeah.
So it's doing this over and over. And so each iteration, is it looking at all of the images as an input, as a reference, or is it going through one by one as it's optimizing? Can you kind of explain that? Hopefully as easy as tangible as possible. So hopefully Jared understands it at the end here.
Sure. Yeah. So the way we do that, we call it actually the principle we call it as analysis by synthesis, which is the goal is to recover the 3D, is to turn those initial points into the Gaussian splats. But how to recover the 3D? We do it by render out we first start with the points and initialize some Gaussians on those points, and those Gaussians could be just a rough guess of what the scene look like. Give it some scale, give each point some scale and some initial density, some opacity, and initial color. And then we render those initial Gaussians out into an image. And from that rendered image, which is a synthesized image, we compare that with the captured image and calculate the difference. And because this rendering process is differentiable, we could calculate the gradient of those Gaussians, basically meaning like how we change those Gaussians to minimize the arrow. Like if we want to reduce the arrow, how would we like to change those Gaussians? Okay, so we calculate those gradients and we apply those gradients back to the Gaussians. Then the Gaussians being like changed a little bit. The arrows should like the difference between the synthesized image and your capture image should be like smaller. And we keep doing that basically. Like we keep rendering out the new Gaussians, compare with the image and the computer gradients, backward propagate to the Gaussians and update that. So that's the basic idea, just analysis, which is to recover the Gaussians, by synthesis, which is to render out the image and back propagate the gradients. So that's the basic idea, but there are also some other stuffs. Like for example, when we initialize this set of Gaussians, we probably start with say like 1,000 points, but 1,000 points, most of the case is not enough to represent the complex scene as we discussed before. So we want to have more Gaussians. So in this entire process, we also would like to gradually introduce more Gaussians into the scene. So we have some logic around that, and also there are some Gaussians after the optimization might end up just very transparent Gaussians, which end up not really useful at all, because it's fully transparent and we don't need to render it out. But there are also process of like identifying which Gaussians are that during the optimization process, and we try to remove those. So we have those add and remove process, and also a splitting process. Like if a Gaussian is optimized into a very big one, we probably want to split it into two smaller ones, because most of the case in the real environment, we have those complex textures, and those complex textures can be better represented using small Gaussians, small, like tiny Gaussians. So there are those different operations in this optimization loop, trying to manipulate the number of Gaussians, or trying to like shrink it, like cut some of them. But yeah, high level, those are the basic elements in this training pipeline. And we just keep running it for a couple thousand iterations, and the things starts to converge. You get some nicely looking Gaussians out eventually.
Nice. So try to repeat to echo some of that back. So it sounds like you're saying, you start out with some blobs, some Gaussians, and then you say, what do these Gaussians look like from a particular perspective? Let me rasterize that. Let me render that. Compare that rendering, compare that synthesis to what I knew my image was. So, I know that someone took a photo from a particular position and angle. Let me compare what was just rendered versus that photo. And then I can compute some difference between that. And because this entire process is differentiable, it means that when I'm able to estimate or compute the error between my synthesized image and my real image, I can take that error and figure out in which direction or in which way I should change that representation, change those blobs in order to get closer to my target photo.
Yeah, exactly.
Yeah. And then you say, okay, well, hey, the blobs that I have, if I only have 1,000, maybe that's not good enough to accurately represent the, all of the complexity in the scene. And they say, okay, maybe we'll add some more, maybe we'll split some big ones. Or if there are some blobs that are just not contributing anything to the overall scene, we can remove those as well.
Yeah, that's right.
So a lot of those parameters can be tuned before you train as well, or you can do it over and over with different parameters to see how well you can achieve as close to ground truth as possible. Right. So I've noticed this, like with threshold, they'll say you started here, but you can make that pruning threshold for when something is near invisible. Let's just get rid of it. So that opacity level can be higher or lower, and you can just see which ones work better for your scene.
Yeah, there are a couple hyperparameters. In many cases, you probably don't need to train those hyperparameters. But if you really want to dig into the detail and want to pursue for the highest quality, parameters like how many Gaussians you like to converge to probably is the most important one, because the more Gaussians you end up with, the better the quality you would get from your 3D Gaussians.
Okay. That makes sense, obviously. More detailed the output, the more detail you can get in your picture. That always comes with a cost benefit. So if you go to say, I want 7 million of these blobs, that's not going to work so well for viewing on an iPhone in real time. So what I am seeing people do, though, what I am seeing these platforms do is I have an SD and an HD version, which is really, they train it probably 2 times or something. Maybe it's 2 different checkpoints. And so they end up with one that's maybe a million or less. And then one's the full 7 million. And the viewing experience for the HD 7 million is really made for a computer with a GPU, not a small handheld device. So they can optimize to, hey, you're going to get the best results on a computer. You're just trying to look at a tiny screen. You'll probably look great too, because you're looking at a screen that's only 6 inches big.
Yeah.
You're going to get the less blobs version.
Yeah, totally. We could have different versions for different devices. Kind of like the old days for meshes, we also have like different amount of triangles for different viewing.
It's the first thing you always do when you got a video game. I remember getting, it was like Crisis, and putting it in insane quality mode, and then just seeing them getting 2 frames per second. But boy, it looked cool for every twice a second. So
I got a cup of coffee and coming back to see, okay, what it renders out.
Yep. All right.
I don't know if this is where you're headed next, Jonathan, but I'm curious because you mentioned, Ruilong, about, you said we do this process, it's iterative, we synthesize and then we analyze and we go back and forth and we do that for thousands of iterations, so thousands of times. That sounds like that could take a long time. So how did you, or how do we make that go fast?
Yeah, That's a great question. So that sounds a lot of iterations, but in the modern implementation, it could run pretty fast. Actually, the each iteration could just take a couple milliseconds. So like a couple thousand iteration could just be finished like in probably minutes. So pretty fast. But the way we achieve that is by just some like kind of hardcore engineering. I actually just put all the computations into the GPU kernels and trying to fuse all the computation into a single kernel that avoids some like heavy kind of memory access stuff in GPUs. But if you are going to implement this thing into pure Python, that will be way slower, like maybe 100 times slower than this. So that's kind of the detail under the hood that we would like to maximize the uses of the GPU by fusing all the computations into the kernel. And that gives us like this ability to optimize the thousands of iterations in just a couple minutes.
Got it.
This is why it's important for people getting into computer vision, computer science, to actually learn to program. Because you can achieve a lot with Python, but you can achieve a lot more if you can optimize and speed things up, or have someone on your team who's good at that. And that, I mean, that's what Jared's done really well for us as well. It's like, hey, we already have a good output, but we would like to do it a lot faster. So there's a lot of thought that's not necessarily around how do you make a Gaussian splat, but how do you make it run fast, which is a completely different,
totally different problem.
Problem.
Yeah.
And that's what NeRFs was. NeRFs was like, hey, we proved it worked in 3 days. Now let's see if we can make it work in 3 hours, and then 3 minutes. And same with Gaussian splats. I think the first one, I have a nice GPU, but even on like a couple years old RTX 3080, I think I was training these things in about an hour. So we're not thinking very long periods of time. However, it seems like everyone online is always like 45 minutes. That's like forever. It's like, well, if you come from a photogrammetry world, some of these data sets took hours. So this is still much faster. A lot of times it was you input your 1,200 photos into your computer, and then you let it run overnight and you see if it actually worked, using one of these photogrammetry software. So to me, and you even can see it converging in real time in the viewer. So you know if it's working or not as it's coming together. Now, if there are a certain point, or maybe even minutes, you know that it looks good enough that just more time, it's just going to look better. Yeah. And it is a lot. I think people need to realize there's a loss graph to this where it's 7,000 iterations, you know if it's going to look okay or not. At 30,000 iterations, it's going to look really good. 100,000 iterations, it's not going to look over 3 times better. It'll look somewhat better. So there is a loss where after a while, each iteration isn't really doing much because there's only so many things that you can continuously optimize.
Yeah. Because the difference is getting smaller and smaller, and the changes that you can make in the environments are also getting smaller and smaller. So it's a long tail effect of the training. Yeah.
And I also notice a lot of times you can set like how many Gaussians you want. So maybe say only I want 1 million. And it might hit that 1 million really quick in the iteration process. So then it's just trying to manipulate and move those 1 million to get to the scene as good as it can get. But I think sometimes you get to that point where if you really want to get better after that, then you have to have more you have to add more blobs. You can't just make these blobs better by reshaping them because there's just a limitation to the amount of geometry changes you can make. So
Yeah, totally.
all right. Well, okay, so I have a few questions. I would love to get into Gsplat, what you're doing there, but I just have a couple more questions, maybe more hot takes from you on this technology. So now we know they're made. Everyone talks about 3D Gaussian splatting. However, the spheroid, the original project uses a spheroid. That isn't the only shape or primitive you can use, correct? So like I've been playing with voxels, triangles, convex shapes. What would be a flat 2D Gaussians? Is there a benefit to using a different primitive? Like, why would I even look at these other versions?
Yeah, this is a great question. So it's also a question that many researchers are thinking, like Gaussians are the final answer of the 3D representation. Like, is it the best choice that we could get? Are there better choice there? So there are papers that came out using like a triangle as the representation to the splatting, convex, and other formats. They definitely have the better representation ability because it's more freeformed. Take this convex splatting, for example. It is controlled. Each primitive instead of a Gaussian blobs is is a convex box controlling the Gaussians. So the primitive have more capability, is more free-formed in that case. So it could represent some, like for example, sharp edges more easily because Gaussians is always just hard on representing some hard edges and surface. So those new representations definitely have better capability, but it also comes with costs. For example, this convex representation, it takes multiple control points as a representation of the shape. This means you need more parameters to represent the 3D, and you need to take more memories when you optimize it, and it also took longer time comparing to optimize purely Gaussian splats. So, and we also know that for typical Gaussian splats, if we just stick with this simple representation, we could always add more Gaussians to improve this overall capability of this representation. Like each Gaussian itself doesn't have the ability to represent like complex shapes, but we could just have more Gaussians and overall its representation capability increase. So there's this trade-off of like having each primitive to be more representative or introducing more primitive to have a better overall capability. And I don't see, so from that perspective, I don't see a clear improvements on top of Gaussians. Like the overall capability is improved with the memory and the runtime in mind. Like if we evaluate under the same runtime and using the same amount of compute, would we get better reconstruction quality with the new representation? That's something I'm not sure, but certainly I believe that the Gaussians is not the final answer because it's just not, it has clear limitations on representing the sharpness of the space. We have to use like quite a few Gaussians to represent a single sharp edge. But still, I think we need to see it from the perspective, of like under the same amount of budget, a compute budget, like is the overall kind of representation is improved or not.
I like to think about it is like, I'm going to pull up an object. I have this USB key sitting on my desk. And to represent that with triangles, it's rounded, it's got all these, you need a lot of triangles for this tiny little object. And so while we have all these rounded edges, which is great, I mean, in Gaussians, it can be less. Well, we still have the same problem because now you got all these things that are flat that, could be represented with like one big convex shape, but we now have to use hundreds or thousands of Gaussians. So it's just, we flipped what can be optimized in the scene because of the shape and the primitive. So I think that's really interesting, That gets my next question. You might be too young for this, but I'm like, are we having what's called a Betamax moment? So I guess for the listeners who might be a little on the young side, there was a point in my life where we all had VHS tapes and all my parents just be like, well, the better version was Betamax. So basically 2 forms of a VHS tape came out and the inferior one won because that's what the industry decided to go with, even though it was not as good as a Betamax. Are we seeing the same thing as I'm starting to see all these third-party software coming out with integrations with 3D.js? So now I can plug 3D.js scenes into like Unreal Engine, things like that. Have we hit that moment where now everyone has said, we're using Gaussians, we're using spheroids, and that it doesn't now matter? We've locked in too much that we can have perhaps, I've been playing triangle splatting. The metrics are, not crazy better. We're not like, oh my goodness, went from standard to high def, but still there might be a better version. But does that even matter? Have we all locked into one? And what is your take on that? Do you think we can still come back from that and have different primitives being integrated? Is it a hard problem to solve to have multiple forms could be from one software?
Yeah, I think the Gaussians is very simple to deal with, to render and to like train. Those are just much more simpler than this complex primitive. But I think it's also interesting to think about this comparison between triangle and mesh, triangle and the Gaussians, because like the mesh representation has been dominating the 3D for quite a long time. And of course, there are better representations than mesh in different perspective. It's still the mesh is dominating the entire field on all the applications. Until now, I think there is some discussion around like maybe this Gaussian splats. Gaussian could be a better way than mesh, like different in many applications. So to like replace the mesh entirely, there's still a long way to go because it's being deeply integrated by all those like rendering engines and workflows. I mean, we probably only going to spend the efforts on the things that we can see a clear kind of benefit. If the benefit is margin, then probably the effort is not worth it. So I feel that only if the next version of the representation is way better on certain tasks than the current one, then it will be like interest on shifting to that representation. But right now, I don't yet see something that is like way better on all the aspects than the current Gaussian splats. So probably that's also why people are just still sticking with the current version in many cases. Of course, in certain cases, if you, for example, want to pursue higher quality, you probably could go for the better versions, but in general, because it's simplicity of the Gaussians as well, and also there already is a huge community built on top of this like simple Gaussian formats. There is this compression, a lot of people working on compressing the Gaussians into a small file format. Small size file format. There are people working on different render plugins like for Maya, for Blender, just very compatible with the initial Gaussian format. So there is already a community around it, and to overrule that needs a big kind of reason, I would say. Yeah.
Well, I like you touching on that again. He's talking about how triangle meshes have been so dominant in the industry, and I guess I think the thought that was coming into my mind is like, well, what is the purpose of this 3D representation? Am I using this 3D representation to try to just create a pretty, a photorealistic image? Or am I? You mentioned before about each splat could have semantic understanding, like, oh, this splat belongs to a couch versus a table versus a chair. Like, am I using a 3D representation to support the semantic understanding of my scene, or am I using the 3D representation to support motion planning and collision detection for my robot, my autonomous navigation of a space? And so I can imagine each higher level like, am I using a mesh? Am I using an implicit representation, a parametric representation of my scene? Am I doing a NeRF? Am I doing a splat? Like, each one's could have its own pros and cons. And then there's subtypes, like you said. Well, within a splat, it's like, well, what is the geometric primitive that I'm using for each individual thing? And maybe it depends on the application. Like if I'm in a video game, maybe the main geometry, the scene, the city around me, that's a triangle mesh. But then, I've got some puddle of water, and I'm going to use ray tracing, on that puddle of water. Okay, ray tracing is a rendering technique on top of that geometry. But like I use a technique that for my reflections, but then I use a splat for my volumetric effects. And so maybe there is, depending on what you're going for, I'm sure there's always going to be pros and cons.
Yeah, exactly. And also those different representation could be used together. Like you could have splats living in a mesh living in the Gaussian splats, and you could do some like fancy retracing on top of that. Sure, yeah, totally. I think the in the content of robotics, when they care about those like geometry more, they still prefer like a mesh more than Gaussian splats. In the content of like lifting information from 2D to 3D, most of the case we prefer splats more because it's friendly to the gradients, to the training, to the optimization. So yeah, depends on the use case for sure. And I think there are also like some use case actually prefer NeRFs, which seems to be something kind of starting to be override by splats. But NeRF is very flexible on like per ray-based formulation. The Gaussian splat is kind of like an image-based formulation. So in some cases, when we don't have image, we just only have like a sparse pixels available, for example, sparse reads available. We would still use NeRFs to reconstruct the 3D. But yeah, I think I could go with this discussion like a lot more, but I think it's just different in different cases. Yeah, I totally agree with that. It's just having different choices.
If you look at some of the projects coming out, you can see that there's different projects that kind of have a different end goal for each one. And they're using diffusion-based methods to use a Gaussian splat to create some initial synthetic data, and then they can use diffusion models and autoregressive models to then predict additional frames outside of that. So it's kind of like saying, we're going to get all this synthetic data, and that's all for like machine perception. Maybe that's the goal there. So maybe they care about things being accurate as far as physics and how things get bigger and smaller and things like that. But they don't really care about a machine having a mesh to collide with in some game engine. They're just feeding it to a machine perception, like an autonomous robot, to learn what that scene looks like in some examples and things like that. So you can see how like they don't care so much as far as those projects care about having a mesh ever or mixing with a mesh, versus other ones where I see NVIDIA as well doing like their drive sim, where they're saying we're going to have a street that we've created with the Gaussian splat. We're going to have a mesh layer that is low quality to give collisions, and then we're going to populate with other mesh objects like cars and things like that. Because we already have those off the shelf. We can plug them into this all simulation game engine, and then have our autonomous system drive through that and learn. And you can throw a dog or a cat and a human out in the middle of the street and see how it reacts, all those things. So you get the soup of all these different, methods all in one scene, which is neat. So it's kind of like, we're not ever saying this is this or that. It's kind of like, you might just need one. You might need them all. It depends on how complex.
The real world application is complex. It's more than just a simple like a novel view rendering task. Always have like more tasks behind it. And speaking of diffusion, it's actually pretty interesting because when we talk about reconstruction, like recover the 3D from images, from captures, it's almost impossible in the real case that we could cover all the viewpoints. Even though we recommend people doing like this 360 kind of captures, but if you want this object to be fully recovered from all the viewpoints, you have to cover all the viewpoints like in the 360 way of this object. This is really hard to achieve when like you have some like structures, for example, behind the wall, you can't capture it. So in that sense, the reconstruction is only like a partial reconstruction. Like we only be able to recover the partial of the 3D. And for the part that is not being covered by the captures, if we still want it to look good, we would need some generation ability on that. So I have this like belief that the reconstruction, that problem that we see in the real life is not a pure there is no pure reconstruction problem. It's always conditional generation problem that you are just conditioning on some of the captured image, which would provide you some constraints on what those viewpoints should look like for the 3D content that you recovered. But there are also other viewpoints that is basically a generation problem. So I would phrase it more towards to the conditional generation problem, since we mentioned diffusion in the real world setting. But of course, like reconstruction is something we need in this conditional generation concept. We need those like viewpoints being perfectly aligned with those captured images, and those are the things we need to reconstruct it.
Okay, so let's take this opportunity then to pivot, and let's talk about then less about just the technology and how it's made and all those questions, and more about you've actually been building around Gaussian splats for quite a while now, and you are part of the Nerfstudio project and also more specifically Gsplat. And I think let's just start off. What's the difference between what is each one, Nerfstudio and Gsplat, and how are they connected yet different? Because I think there's a lot of confusion when someone says, "Oh, did you use Nerfstudio?" I said, "No, I use Gsplat." And they're like, "Isn't that Nerfstudio?" I said, "No, it's no, but yes."
Yeah.
So, can you help us figure out like what is this that you've been working on for Gaussian splats, and how are they connected and not connected sometimes?
Yeah. So this comes back to the story of how Nerfstudio started. It started as a project for Nerf, and a lot of design here are for the Nerf representation. Until like Gaussian splats came out in 2023, and we feel like okay, we also want to support Gaussian splats in Nerfstudio, so we start to this efforts of trying to bring the Gaussian splats into it. But there's also issue with the implementation for Gaussian splats, because that's pretty hard to do it in Python, pure Python, and it could be very slow. So we need some like a dedicated CUDA implementation for that. So that's how we start with this kind of separate repo called Gsplat. We just want to put all the CUDA codes in it, so that when people install the Nerfstudio repo is not like, and if the people do not want to use Gaussian splats, they don't have to compile all those CUDA code. It's just to make it an optional kind of dependence of the Nerfstudio repo as the beginning. Then many of the implementations and develops happens in this Gsplat repo, and we see Nerfstudio as as a repo that we would like to ship whatever we developed in Gsplat into it. So that's the initial design. Like we also we have this like a Gaussian splat factor. I think that's the name, supported in Nerfstudio. And that is basically importing the functionalities from Gsplat and use it in a way that is compatible with the Nerfstudio repo. And the nice thing is that it could benefit from all those data format supports in Nerfstudio, all those export supports, all those viewer supports in Nerfstudio. And the underlying is just calling the CUDA code from Gsplat. But over the time, start to get harder and harder to sync all the developments, all the up-to-date developments from Gsplat to Nerfstudio. And things move so fast, we have to keep adding new things, keep doing like some CUDA changes. Mm-hmm. And syncing those two becomes like really hard, because the maintainers of this project is just students at UC Berkeley. We don't have too many manpower on this. So at this point, we have kind of make a decision on trying to shift more focus onto this Gsplat repo itself, because like we see that going forward, the Gaussians itself is going to be more and more popular, and trying to sync between the two is just getting harder and harder. But there are also some benefits using things from Nerfstudio side, because we have viewer and complicate like a complete support for the format stuff. So going forward, we're probably going to factor out the viewer from the Nerfstudio repo, so that itself could be smaller, more independent sub-module, sub-repo that people could import and use in different projects. Actually, not only for the Gaussians, probably for other cases, you could also use the amazing viewer from Nerfstudio, and also the data sets part in the Nerfstudio, we probably also going to factor that out so that people could support different formats, not only for Gaussians. That means that the Gsplat repo probably going to be the most up-to-date supports for the Gaussian splats, and we could also benefit from those data supports, viewer supports from Nerfstudio if we factor those things out. So yeah, that's how the current thing look like. If you want to use, so in the current stage, because we haven't done all those factoring yet, if you want to have a basic Gaussian implementation and want to have those like data supports, viewer supports, I would suggest to go for the Nerfstudio repo. If you want to try with those up-to-date latest ideas on Gaussians and you are fine with having those less support on those extra features, then I would suggest with the Gsplat repo.
That's really helpful. I think people don't know which one to start out with or stick with.
Yes.
It's kind of like Nerfstudio came first, right? You said for Nerfs. Then you had to integrate splats. And so then it's kind of like a sub-module that Nerfstudio wraps around or draws from. I don't know what the right terminology is, but saying, hey, we want to now do a splat. Go use Gsplat. It's just hidden underneath there. You just don't see it explicitly. Then it does that, and then it can leverage the viewers and all that. But now, yeah, I've noticed at the point now I have two different environments, one for Nerfstudio specifically, and one for Gsplat, because Gsplat has kind of, it's like all of a sudden they put the gas on the pedal and they're going too fast for Nerfstudio to keep up, and so now they're not necessarily compatible with all the different versions. So I have two. I can run Splat Facto, which is really easy. I think that's the easiest way to make your first one is just get Nerfstudio and run it's called Splat Facto, and you don't have to really give it very many parameters.
Yeah, Nerfstudio is kind of designed for new players in the game with pretty good documentation, tutorial, and like the APIs, how you launch the code. So if you are a starter that wants to play with this technology as the beginning, then Nerfstudio is a good place to go. And the Gsplat is more kind of developer-facing and researcher-facing kind of repo in the beginning. Even though now we are also trying to make it more friendly for the beginners, but still it's not as good or like away from how friendly it is in Nerfstudio repo. Yeah.
Mm-hmm. Yeah, and you can interact with these in different ways, right? Like you can use command line, obviously, and then kind of start off training and use a viewer to look at it, or you can completely do all command line all the way through.
Yeah.
Or you can through Python and things, whole different parts. So it's really, really nice as a developer. And then it's all permissible licenses, right? So it's not like this is cool, I want to put this, and then realize, okay, we're gonna have to start paying the piper if we want to build a project around this, because we have to immediately license it and start buying anything like that. But this is more of I like this. I just have to abide by the permissible license rules. But
that's something we're trying to stick with, the Apache 2 license, which is permissive for both commercial and researchers. The entire Nerfstudio project, we're trying to stick with this license. That's also part of the reason that we start this Gsplat repo, which is in-house like a re-implementation of the Gaussian splats, and because the original code base was released under more strict license.
Oh yeah, the original one, yeah,
the original one, and we want the entire Nerfstudio ecosystem to always stick with permissive license. So we start this efforts on our own implementation and end up with the Gsplat repo. And we put a lot of efforts on optimizing it, actually. So I believe currently is runs faster and uses less memories, and also comes up with more features than the original one. And going forward, I think we'll keep maintaining it and developing on it. It's a pretty good place to get to know all those like the latest stuffs happening in Gaussians, because there are also plenty of like amazing researchers kind of hit this PR pull request in the repo, trying to contribute their latest works. So not only in this main repo you be able to find the new technologies, you also be able to find some interesting things in those pull requests panels that's from the entire community.
Yeah, and that's such an amazing thing, and important. The importance of that cannot be understated or overstated, whatever the phrase is. But like, it takes something to be a good engineer or to be a good researcher, like to actually write code that can go fast or to come up with new algorithms that, advance the state of the art. It's a whole nother skill set to figure out, well, how do I document this and package it and actually present it to the world so that other people can use that work? That in itself is a whole host of effort to do that. And it is so foundational, fundamental in that it helps the computer vision community, like how CallMap, when Johannes, he developed CallMap and then, it's got some other people involved, but Johannes, that open source that. Now everyone can use CallMap. And now when everyone thinks, oh, I need a point cloud or I need camera poses, I'll use CallMap because it's freely accessible and permissively licensed. And so that now has been like the go-to tool for a lot of tasks. Similarly here now, having these nice implementations, well-documented, beginner-friendly implementations around NeRFs or splats. That's so helpful.
You created the whole map of radiance fields. The impact on the world, you and the everyone working on that, it's going to be, it's what I think is really cool is that I'll see something new come out. I'm like, oh, it's really cool. Hopefully, like one day that gets implemented in Gsplat, so it'll be open source, and I'll put something like that on a tweet because that's what likes like that or whatever it's called nowadays. And then they'll say, oh, I already have a PR in there. It's kind of like they want to be in there. So it's got to that point where it's like, well, that's the obvious place I want it to be built if I want people to use it outside my research.
Yeah,
and test it and.
Going forward, I would really like to push this repo into a place that could centralize the efforts of the. I think that's also the initial idea of this. I was trying to modularize the different implementations so that I could easily add some new features to it. For example, this multi-GPU support could be implemented. We already implemented that in Gsplat, where you could just leverage more than one GPU to reconstruct the scene and give you substantial a speed up and enable you to recover a way larger environment than you can do using a single GPU. And that's from a paper from a system group, not doing too much on the 3D research, but more on the system side. And we'll be able to implement that in Gsplat with a couple line of Python code pretty easily because entire Gsplat is designed to be friendly on introducing new features by modularizing different components. So we have Python APIs on top of CUDA implementation for different components in the Gaussian system, in the Gaussian Splat training system. And we were hoping initially those set of Python APIs could alleviate the efforts for researchers and developers to spend on developing new algorithm on top of the original Gaussian Splat algorithm. We could have some building blocks basically for the Python-based developers could take those building blocks and create new, better algorithm on top of it. That was the initial design. So we, based on that design, we were able to absorb those new ideas into the same code base. So Gsplat now has many features, but also there are also some new designs that is actually hard to integrate into the whole system, and there are always some conflicts between this design and the other design, and is sometimes you have to make the choice of which one to support and which one not. So a better way going forward maybe just have a list in the repo that indicates there are also some amazing works out there that unfortunately we won't be able to integrate into Gsplat, but it would be nice to have a central way for people to see what are the coolest parts happening here and their implementation in this Gsplat in this Nerfstudio ecosystem. And if you have the knowledge about how Nerfstudio works, how Gsplat works, how those things are implemented in those repos, it might be fairly easy to also get to know what the changes for the latest works are doing and what the benefits spring from that.
Mm-hmm.
Yeah, going forward, I think we are trying to also build that so that both the starters could do not have to burden all the complicated the system in the same place. If they don't care, they don't have to read those things. We would just separate those things out.
All right. Well, it's exciting to watch this develop. I feel like Gsplat was slow at the start because they were just trying to get the foundation in. Now it's like it's updating faster and faster.
Yeah, it's growing.
GPT came in, that was pretty exciting, and it's cool to see these big projects being announced at the same time. They're already integrated in Gsplat. Like they started out with that goal, we want this part of the project, as opposed to, we'll get around to it one day.
Yeah. So some stuffs are kind of rather easier to integrate than others, so we could just integrate them pretty fast. But others requires more changes to Gsplat. Those could probably came later.
Mm-hmm.
And we also need to figure out the backward compatibility issue. We don't want to break things up for users already using it. So yeah, I guess it's mostly also for the users on the Windows side. By the way, thank you, Jonathan, for making this tutorial for the Windows side users. Personally, I'm not a Windows user, so I feel like sometimes the Windows support might be out of sync and is not in a great shape. But we also trying to consider the requirement from Windows side that we are trying to support Windows as well going forward.
Mm-hmm.
Because we see a lot of users on that side as well.
All the developers are on Linux. All of the people in industry who want to monetize it are on Windows. So go figure. But then the developers they have within that team probably have Linux. But it's the people who want to play with it and understand it probably on Windows. People who are wanting to build with it are fine either working in Linux or already that's where they are. And I'm in the boat now where I have Windows, Linux, and a Mac, so I can jump in whatever operating system I want. I'm actually falling in love with Linux because it's so much fast. It's just there's not as much bloatware on your computer. Windows is a very large piece of software that takes a lot of resources just to stay on there. Linux, I mean, when I'm idling it, I have nothing open. It's like almost nothing's happening on my CPU or GPU, and things just move fast and just compile much easier than having to use Visual Studio.
I hope at some point we just have one operating system.
Well, on that note, I think we'll wrap this up. I mean, it was an absolute pleasure to have you on here, Jared. I feel like, did you learn something? I learned something.
Absolutely.
There's always something new here. I'll learn. Even me, who's been steeped in Gaussian splatting since I think the second I saw it. I will continue to make tutorials for Gsplat as I see new things come out on it for sure. But I just wanted to say thank you, Ruilong. And if people want to follow along, obviously I will link Gsplat, that whole repository, in the notes to the show so people can go find that. But if they want to follow you and not your project necessarily, are you on social media? Is there somewhere people can follow your work?
I guess people can find me on Twitter, also on GitHub. And those are the major platforms that I use. Connect with outside worlds.
I think it's amazing that I can go on Twitter or GitHub and I can ask a question and I know it's you answering it, which is just incredible. The access to experts, right? And it's, the nice thing about Gsplat too is it's actively maintained by a group of people who are very involved in it. So I can ask a question and it's not like, well, let's just hope someone checks their GitHub notifications one day and see that someone on an old project has asked a question. So it's been great to be able to ask those simple questions and get a quick answer, or at least you point me in the right direction.
Yeah, we also want to collect more feedbacks because that's also how we know that we can make things better and what other things are missing. So totally. I go through the most of the PRs and also the issues. Some of them might be out of my experts, honestly. But I'm trying to see what we could do to get this repo better. Yeah.
Great. Yep. And I always do my part trying to jump in there, answer questions, and I know I can answer them. Someone will say, like, why is that not working? I'm like, no, there's nothing to do with code. That has everything to do with how you captured it. So let's talk about that. I think there's always this thing where they just think, I'm not getting good results. And they think it's because they ran the software wrong. Well, there's not a lot of ways you can run it without it not working. Like it's gonna work. It just might not get you.
I think we can just post some of the app songs. Of this to those questions.
Yeah. So that's where my expertise comes in. It says, send me your image set. Just take a look at what you sent. what's in there. No parameters will recover bad images. So, yeah. Well, thank you as well, Jared, for jumping on and help clarify some of the explanations. And really looking forward to kind of continuing on this thread on Gaussian splatting and ratings fields. I know it's moving fast, and I think we need to do some more episodes on diffusion models specifically, because I think like 5 were released this week, or 4 are around Gaussian splatting and diffusion models, and also around just foundational models for 3D reconstruction. Because I also tried on the fly NVS, which was uses a foundation model to speed up your pose estimation, and I think I went from images to training, not images and a point cloud, just from images to training. I think 77 seconds did a scene that took 45 minutes in the old one. Results weren't as good, but they were really good still. And I think that was something we want to keep talking about. And
that be useful in the future.
Yeah. So, all right. Well, thank you, everyone, and I will see you guys in the next episode.
Thank you for having me.
Thanks for being here.
Awesome.